Welcome to NASA's Jet Propulsion Laboratory. We are in the gallery above the clean room in the spacecraft assembly facility to watch a spin test of NASA's Low-Density Supersonic Decelerator, otherwise known as LDSD. Now, we invited the media to watch this test today, but we also wanted to have the public have this opportunity to get their questions answered. So we have this streaming on NASA TV, Ustream, and also Periscope, and we will try to take your questions as we go along today. Now, that flying saucer-like vehicle that you see behind me, it's designed to test future technology to land bigger and heavier things on Mars. We did a test with this type of vehicle about a year ago in Kauai, and we are going to go ahead and get this play-by-play from the principal investigator of that test and of LDSD, Ian Clark. Let's take a listen.
On June 28th, NASA's Low-Density Supersonic Decelerator project conducted the first shakeout flight of a new way of testing technologies that will one day be used to land heavier, more massive payloads on the surface of Mars. We used a large 34 million cubic foot scientific balloon to hoist a 7,000-pound test vehicle to an altitude of 120,000 feet. The test vehicle was then released from the balloon, spun up for stability, and a large solid rocket motor accelerated to over 4 times the speed of sound in an altitude of 180,000 feet, a condition very similar to the conditions it would see at Mars. Once we reached the correct speed and altitude, we despun the vehicle. And then we got a chance to test our new supersonic inflatable decelerator. The camera lens covers deploy. We see that inflated very uniformly without disturbing the vehicle too much. And now we're seeing previously unreleased high-definition, high-resolution, and high-speed video taken during the test. We used the supersonic inflatable decelerator to slow us to something closer to 2.5 times the speed of sound. We use a balloon to help deploy the new supersonic parachute. The balloon is shot out the back of the vehicle at over 200 feet per second, and then we cut the balloon free and it begins to pull the parachute off the back of the vehicle. As the parachute begins to inflate, we see one of the surprising aspects of this test, which is the early onset of tears in the parachute. We see where those tears began, how they propagated, and otherwise how the parachute behaved as it began trying to inflate behind this very blunt object moving 2.5 times the speed of sound, punching a hole in the atmosphere and creating an extremely turbulent, chaotic environment for the parachute to exist in. We now have a data set that we will use to prepare for 2 more tests beginning in June of 2015.
Now, the LDSD mission is part of NASA's Space Technology Mission Directorate. With me right now is the Associate Administrator of that Directorate, and with me is James Reuter, who is with this Directorate. Tell us a little bit about this. Why is NASA focusing on this next generation of technology?
Well, currently we could only get about 1 metric ton, or about 1 ton, to the surface of Mars, and that was done with MSL, and it's going to be done again with Mars 2020, which is the current upcoming planned mission. Beyond that, if we want to do more capable science missions, or eventually to put humans on the surface of Mars, we're going to have to be able to put much larger payloads to the surface of Mars than we can today. The technologies that are used on MSL are essentially Viking-era technologies, and we've pushed them to the limits of what they can do in terms of mass to the surface of Mars. In order to go beyond those, we need new technologies, and some of those technologies are represented here in the LDSD testing. So both the supersonic inflatable aerodynamic decelerators as well as the supersonic parachutes will be able to take those payloads up to between 3 and 5 metric tons, so multiplying the amount we could do today by up to 3 to 5. And that's on the pathway or on the stepping stones to be able to put eventually humans on the surface of Mars.
And let's help people understand. You're basically sort of starting at square one with this new generation, which means you have to figure out a method of testing these new ideas because the Viking era type of testing mechanisms don't work anymore.
Well, so we had, in the Viking era, we primarily used a supersonic parachute, but that particular design of the supersonic parachute cannot really be made bigger than it is today without substantial risk in whether it would work or not. And many question whether you could build a parachute of that design. To get beyond that payload to the surface, you need to have more drag, larger area parachutes, and or larger area vehicles. And so one approach is to actually have inflatables that pop out on the side of these vehicles, which we've never done before for landing purposes at Mars or deceleration purposes at Mars. So we're going to test different ways of popping airbags out the side so that the footprint of the vehicle as it goes through and tries to slow down in the Mars atmosphere is bigger and therefore produces more drag, and you could put more mass on the ground. Additionally, we're doing a new parachute design that is about 3 times the area of previous parachutes that we were able to design so that we could substantially increase the amount of drag that we could get out of the parachutes as well.
In many ways, this is sort of a behind-the-scenes peek at how NASA comes up with technology. In the past, people usually just see Mars landings or launches of spacecraft, but they don't see the step-by-step meticulous things that NASA has to go through to fine-tune and figure out the technologies you need to get where you want to go.
So NASA has 4 big divisions within it. It has the Human Spaceflight Division, it has the Aeronautics Division, and it has the Science Division. The 4th division is the Space Technology Division or Directorate. And the Space Technology Directorate is geared specifically to developing technologies for future NASA missions in science and for human exploration, as well as the commercial space sector, to allow for an improvement in capability, whether that is to perform better science, for improve the telecommunication satellites that we operate in the U.S., or to do better human exploration, get humans to other destinations such as the surface of Mars. In order to do that, technology drives that initiative, and so that's why we're investing in this technology as well as many others in an overall portfolio of technology advancements that are needed to enable those missions of the future.
So let's talk about technology. In order to create new things, you're going to have to push the envelope. And in that video, we saw that parachute tear apart. And that was not regarded as a bad thing. Why is that?
Now, during that test, it was really supposed to be a shakeout test to see that the vehicle, to get the balloon that carried it to altitude, the rocket motor so that spin it up, the main rocket motor to accelerate it to Mach 4, and then the various other elements of being able to take video and so forth from that vehicle all worked fine. In addition to that, we put preliminary designs of the SIAD, which is the supersonic inflatable, as well as a preliminary design of the parachute on there. We knew that we were going to take a risk in order to fly those components. And in fact, if you think about technology testing and demonstration, the reason that we do these tests is that we don't always know how these things are going to perform, especially in a supersonic environment like this where it has to pop out and inflate, and the dynamics of that are very difficult to predict. So in many space technology instances, the testing, we don't necessarily expect everything is to go well the first time. And so we plan for multiple tests. So for example, the test that's coming up this summer and the test that will happen next year and next summer were already planned ahead of the test that we did last summer. We weren't terribly surprised by the fact that we had a problem with the parachute. In the course of the time period between that failure and the testing that we'll do this summer, we've put in multiple design changes to the parachute and tested it at lower speeds to show that, in fact, it could handle the loads. But the proof will really be to see that we see that a successful test this summer. And in fact, when you think about parachute testing, we always say for another parachute to go to Mars that we have to have 2 successful tests without shredding the parachute to say that in a relevant environment, in other words, in a condition that mimics what would happen at Mars, to say that, in fact, we have a good parachute that we have confidence in to go fly. And so that is why we plan on doing a test this summer, which we hope will be successful, as well as a test next summer to establish the credibility of the parachute design as well as the supersonic inflatable decelerators.
So we're taking what we learned from last year's test, incorporating some of that knowledge into this vehicle that's going to be flying in June, and then we keep on learning from there.
Right.
All right.
So the parachute design, we actually changed it. We strengthened some of the elements of it. We changed the manufacturing tolerances, and we changed the shape of the parachutes, which we think will take care of the problems that we saw last summer.
Fantastic. Well, we promised social media that we would give some
Sure.
questions to you. This one comes from Facebook. It comes from Gregory Gosseb. And here's the question. If this flying saucer test turns out to be successful, does that mean there could be manned missions to Mars possibly in the future, given one of the key challenges is carrying heavier payloads of equipment and crew members themselves?
Yeah. As I talked about earlier, currently we could put about 1 ton to the surface of Mars, whether that's a science experiment or anything else. And we could do that using the same technologies that landed Curiosity there. With these new technologies that we're doing in LDSD, we think we could increase that payload to the surface of Mars to about 3 to 5 tons, which is a substantial increase. However, we think of it as only a pathway to eventually being able to put humans on Mars, because the expectation is to be able to put humans on the surface of Mars with the equipment that's necessary to survive there for a significant period of time. We think that we need to have as much as 10 or maybe even 20 metric tons to the surface of Mars. And so this, you could think of this as a stepping stone, and understanding the technologies to get us part way to the ability to land payloads on Mars. And certainly we have to take this step before we eventually get to a capability that could put 10 or more metric tons to the surface of Mars.
So baby steps to the big step.
Well, this is still a big step.
Okay. This is a big step. All right, James, thank you so much for joining us and filling us in. Now let's take a look at the test vehicle one more time, get a closer look at it. Let's fill you in on it. It is 15 feet wide, 7,000 pounds, and it's sitting on the spin table right now. You can see it spinning slowly there. And right now in the clean room is Paul Lytle. He is standing by. He is the LDSD Integration and Test Mechanical Lead. Hey, Paul.
Hi, Gay.
So tell me a little bit about what's going on in the clean room today.
Yeah, I'm here in the JPL Spacecraft Assembly Facility, High Bay 1. And this is actually the same room in which the NASA Curiosity Mars rover went through its final assembly, integration, and testing, and then preparations for shipment out to the launch site in Kennedy Space Center in Florida. Interesting thing about rooms like this, you have to wear clean room garments, because the biggest source of contamination in clean rooms like this is actually the people. So all personnel that come into this room are required to wear clean room garments like this that minimize the spread of things like skin cells and oils from your skin, lint from your clothing, keeps that stuff from getting onto contamination-sensitive hardware that we have in here. Another benefit of these kind of garments is they're made of special materials that actually dissipate static electrical charge. So if you've ever kind of rubbed your feet on the carpet and zapped a doorknob, you can imagine that could actually do some either immediate or latent damage to sensitive electronics, and we need to avoid that. So this affords protection against that too.
So tell me a little bit about today's test. What exactly will be going on?
Yeah, so behind me here you can see the NASA's Supersonic Flight Dynamics Test Vehicle, and I'll get out of the way here so you can see it a little better. We've got our vehicle mounted on this spin table. So what we're doing here, if you've ever seen a mechanic balance a wheel, what the mechanic does is he'll actually spin the wheel and measure the amount of wobble in the wheel as it spins. and then the mechanic will install small masses around the perimeter of the rim in order to balance out the wheel so that it spins smoothly. We're doing something actually very analogous here with our 15-foot diameter version of a wheel. This spin table here is instrumented such that the sensors inside the table are actually measuring the mass properties of the vehicle and providing the information that our engineering team needs in order to calculate specifically where we need to install small masses around the perimeter of the vehicle in order to ensure that when our vehicle spins, it doesn't wobble and we actually achieve the desired trajectory that we need to accomplish our mission this summer.
Well, Paul, not everyone understands why the vehicle spins. Can you explain that to them?
Yeah, absolutely. Yeah, so in flight, we spin the vehicle for a very different reason from why we're spinning it now. Right now, we're spinning the vehicle in order to measure its mass properties. In flight, we actually have small rocket motors, 8 small rocket motors on the vehicle that are going to spin the vehicle up to about 60 revolutions per minute, about 1 revolution every second. And it's really following kind of the same theory that is used. It's the same rationale for why bullets and arrows and other objects like that spin. It actually stabilizes the vehicle in flight. If you think of a top, of a toy top, if the top's not spinning, you could theoretically balance it right on end and it wouldn't fall over, but that's very difficult. If the top's spinning, it's actually much more stable. So it's sort of the same principle that we're taking advantage of here.
And let's help the viewers get familiar with what they're looking at. Can you describe the entire vehicle and where things are located on it?
Absolutely, yeah. So starting at the top, you can see that's the kind of the windward direction. That's the direction that we fly, and that's the heat shield of the vehicle. Now, this test vehicle is a full-scale representation of the kind of vehicle that would enter the Martian atmosphere and deliver a payload to the surface of Mars. So it's a very similar shape to what we would have in a real flight vehicle entering the Martian atmosphere. You can see it's painted white for thermal reasons, and we've got actually an ablative layer there of quark on the top there, and that is designed to burn away and carry some of that heat energy away from the vehicle as it flies at the edge of space in our test this summer. Moving down, in the biggest diameter there, that's the shoulder region. The aerodynamic flow will separate from the vehicle around that vicinity, and then you could see this yellow-colored material here. That's actually Kevlar, and that's used to restrain the SIAD, the supersonic inflatable aerodynamic decelerator that we're trying to qualify for use on Mars in future missions to Mars. And then on the bottom here, this brownish material, that's more thermal protection hardware. And you can see this telephone pole-looking device here that actually houses a lot of our instrumentation, our cameras suite that'll be observing the deployment of the SIAD and also the parachute coming out the back. And it's got kind of a black box on board that archives a lot of our data.
Can you give folks a preview of what they're going to be able to see today? When do you think we'll see this spin test at full speed, and how long will that be? Yeah, so they're right between tests right now. They're just wrapping up one of our product of inertia spins. They'll be actually starting the next one momentarily. It takes a period of time to spin up, but I would estimate in about 30 minutes you should see the vehicle spinning close to the fastest that we will get to in this test, which is about 30 revolutions per minute. All right. Paul, I have a Twitter question for you, and here it is. How do they keep it stable and flying in the right direction? Yeah, that's an excellent question. So this kind of goes back to what we talked about regarding bullets and arrows. The reason that bullets don't tumble as they're flying is really because they're spinning. So we're using that same principle here. We spin our vehicle up before we accelerate it, and that enables us to fly in a very straight trajectory and to reach the desired conditions to represent the kind of conditions future vehicles would be in when they enter the Martian atmosphere. All right. Well, Paul, thank you so much for being our reporter on the clean room floor. We will check back with you as we get more and more Twitter questions and social media questions. Thanks for being there for us.
Thank you.
All right. So let's go back to the test. We saw the test back in Hawaii a year ago. We learned from it. And now the team is taking that information to build upon this new test that's coming up this June. Did I say January? It was June. And with me right now is Rob Manning. He is the LDSD Chief Engineer. And also with him is Grace Tan Wong, and she is the Flight Operations Manager. So we saw that video from Ian Clark, and he gave us the play-by-play. But what we're hoping to learn from is where to from now. What did we learn? And we've got the video for you that takes that footage from the spin test on, and we can actually roll it right now, and you can kind of fill us in.
Okay, well, last summer was, as we already talked about, was our shakeout test, and this is one right happened here. You can see the vehicle spinning up very quickly just after it dropped from the balloon. The rocket fires and pushes this vehicle from basically the same altitude that you would be at the surface of Mars if you were at Mars in terms of the density of the atmosphere. Once the rocket fires, it pushes it even higher than the balloon to a point where the air is thin, just like at Mars. Because remember, what we're trying to do is we're trying to take this vehicle and find a place on this planet that is just like Mars with respect to the thickness of the atmosphere. And the place to do that is well over 120,000 feet, 3 to 4 times higher than an aircraft flies, an airliner flies. So you're way up high. Once you're there, you can do the test. Now, once we're up at 180,000 feet, where we inflate our SIAD. You saw that happen a moment ago. Now we have this balloon device, which is a device to pull this big parachute out, and you can see it did this job perfectly. But once the parachute came out, things didn't go so well. The parachute didn't stay together as it inflated. And so this test was a test of our test system. We put the parachute on there, obviously, to see whether or not maybe we can get lucky and everything works perfectly. And it did up to the point when this parachute opened. So what we've learned is that there is something about inflating a parachute supersonically, like we've done at Mars many times before, of this scale and this size and this shape and this particular configuration of parachute that isn't happy with inflating at those speeds. And in particular, because the air is so thin at Mars and so thin up at 180,000 feet above our planet, the parachutes open up much faster. They open up, on Earth, a parachute opens like this, slower, then it gets to the point of full inflation where the full loads are on the parachute. Well, fortunately, at Mars, there's a big difference. Because the air is so thin, it doesn't take much to get that fabric really racing out. So we have this 31 meter diameter parachute opening up really fast. In a matter of a fraction of a second, it goes from a line of fabric to its full open condition. That speed, we believe, had something to do, as well as the shape of the parachute, of causing that parachute to fail. So after the failure, we sat back and said, what the heck is going on? And so by studying the video, studying the pattern, looking at the speed, looking at the high-speed video, the stuff that was so high resolution, so we could see the actual details of what was happening, we realized that we probably, for this test, we used something called a disc sail parachute, and we can come back to that in a minute. But we decided after that test that we should do something different.
Well, let's talk about what you learned. You were able to take a lot of that data and turn it into a visualization that you created, where you could actually track the balloon going up and deploying things.
Well, what's so cool is that you can see in this video, you can see this wonderful shot. The blue line is the trajectory of the balloon that we recorded using a GPS system from the launch site. From that runway down on the west coast of Kauai, all the way up higher and higher. You can see how high this balloon got straight up and finally got to the very high upper winds way up above the troposphere, which blew the balloon out over the ocean. You can see how far it goes. At our particular point, we dropped the vehicle and fired the rocket, and the rocket took the vehicle in this giant arc way up about 180,000 feet. And you can see just how big this flight is and how much of an ocean you need. So we really count on this vehicle, the balloon, taking us out over the ocean, and we have this wonderful flight, in many respects simulating the same kind of trajectory that a vehicle entering Mars would have, and except that the surface of Mars is about the altitude of where the balloon is, where the balloon's taking us to about 120,000 feet. So with the data of the trajectory, the data we collected from the video, and all the dynamics information, we were able to, in detail, reconstruct really what happened last summer. And that information we put all together to help us understand what happened with that parachute. And why did the parachute come apart well before it even got to the point of full inflation?
So, Grace, why don't you fill us in on what the difference this test will be compared to what happened last year then?
Well, as people have mentioned, this last year was a shakeout test, and we were able to show that this was a valid way to be able to test this technology. And we got the added bonus of at least testing out the SIAD. And this year, we're back again to get a successful, or at least understand better what the parachute is. And so we set up this ConOps, or concept of operations, just like we would for a flight. We work with multiple teams. We have a counterpart at Wallops, and we work very closely together with the Navy to pull together a multi-organizational team. And together we fly an operations much like we would on a flight project, because we have one shot. We have this one vehicle, that a very valuable resource, and we want to make sure this technology gets tested out correctly.
We can actually show what it looked like there last year. We have the control room, and it looks like an MSA to me.
Exactly. So this is our test vehicle. It's a Navy range, so we only were limited to be able to film certain areas. But this is our test vehicle operations. And just like a flight room, we have the back row here. This was our flight director, George, and he led our test vehicle team. We powered on. We had a very set of sequences we needed to turn on and get the test vehicle ready for the flight that Rob just explained. We have our Wallops teammates there, powering, sending commands. We have a systems engineer there next to George, making sure everything was functioning correctly. There I am at the edge there. In the front row, we also had our subsystems, instrumentation, the GlenMac, our phase, understanding how the sequence was going to run, our trajectory analysts. And so we had a full-up operations team making sure every piece was working correctly so that we could get the technology tested.
So this basically operates like a mission. So you have a flight director, you have people there standing by. Do you do the same thing that we always do with missions? We call them ORTs. You know, they're sort of a practice go-round of what every person will go through on the day, on D-Day, on the day that everything has to happen.
Yeah, game day. We want to make sure everything happened just right. And in fact, we had the added challenge on a flight project. We get test beds. We have different places we can actually practice, the operations team can practice on while we're putting together the flight vehicle. On this one, it's a technology demo. We don't have many different other practice venues. We're practicing on the flight vehicle. And so it all came together where once the integration team put the vehicle together, as you saw Paul testing, we sit down with the operations team and we run through. We practice the nominal on a good day. We practice just in case. What if something doesn't power on? What do we do?
Sure.
We understand all the what if cases, and we practice weeks just leading up to the actual game day. And then we interact with the range team. They own the operations, and so we have to know how to interact with them, with the balloon team. There's a whole team on the balloon side making sure that the balloon gets put together and laid out and inflated, and it takes us to the altitudes that we're looking to test at. So everybody has to work together. We practice that and then make sure everything works out right.
So, Rob, the focus this go-round, then I believe, as Grace had mentioned, the SIAD worked perfectly. So the focus now is the parachute, and we have new designs. I guess last time the test was on the best we had, basically, wasn't it?
Yes. Well, what we had done was we took the design of the Mars parachutes we used before. Mars parachutes in the past have a big piece of canopy on top of it, and a single gap of air, a air gap, and then a band of fabric. What we just wanted to do was we wanted to integrate the best of that design with something called a disc sail. This picture you see right here is a disc sail. And what that is it has basically concentric rings of fabric that fill up, and they look like little, and there are hundreds and hundreds of them that go all around the vehicle in a concentric pattern. On the top is a single piece of fabric with a hole in it, and that orange color you see there was the disc, very much like our disc gap band parachutes we've flown to Mars before. We thought this would be a good compromise between something called a ring sail parachute, which is used a lot for terrestrial applications for slowing down vehicles subsonically, with the Mars design. Well, we did that, and we realized that there were some architectural features about that may not make it the strongest parachute, and certainly it wasn't the strongest we expected it to be. So we decided, let's bite the bullet. Let's make this the strongest parachute we can imagine using something called ring sail. So a ring sail parachute looks a lot like this other parachute. It has the same concentric rings on the outside, but in the inside, all the way to the middle, are more of those concentric rings going all of fabric going in. So this has got almost 2,000 panels, individual panels of fabric that are connected by, they're held together, sewn together on pieces of Kevlar. Structure that holds this parachute together. So we believe this parachute is a lot stronger than the parachute we tested last summer. The question is, will it be strong enough? And we did do a test just a few weeks ago where we tried that out.
All right. Well, we'll get to the type of testing that we go through to prepare for the Kauai test. But meantime, I have a couple of questions from the social media. First question is, why saucer-shaped? What's the benefit to have this test vehicle in a saucer shape?
Well, in some respects, it only looks like a saucer because it's supposed to be a space capsule. I mean, space capsule, just like the Dragon capsule SpaceX uses, the Constellation, the Orion space capsule, the Apollo space capsules of the 1960s and 70s, very similar architecture, a big heat shield and a kind of a conical aft body, the back part of it. So the whole heat comes in heat shield first. Now the reason this thing has this kind of flat shape is because we lopped off the back of it. We didn't really need it. We wanted to be able to have a full view of our parachute behind us. So we literally chopped off the back of the vehicle. So that's why it looks more like a flying saucer than a space capsule. But it is a space capsule.
And Grace, can you explain, we see that it is a heat shield, and you need a heat shield coming into Mars, but why didn't you just design a bigger heat shield?
Well, we're limited by our launch vehicle capability. Right now, we've capped out on how much volume or area we can fit inside the launch vehicle. And so what's great about this technology is that it can tuck in when we're being launched on our way to Mars, for example, but then inflates to increase our area when we need it to enter into the atmosphere.
One more question here from Ustream. What is the G-force exerted here?
In this particular vehicle, when the parachute opens up, it produces a very large, very short duration deceleration, something in the order of 10 or between 10 and 15 Gs of deceleration normally. And that's been typical of all of our Mars vehicles. Now, it's a little rough for a human being, but for a robot, it's pretty good. And robots don't mind. Now, and that's comparable to the deceleration you feel when our robotic vehicles are entering the Mars atmosphere, just with a heat shield. Earlier on during the entry process, the E part of entry, descent, and landing, where they're using the heat of re-entry to slow down the vehicle. So it's about that. Now, when humans go to Mars, obviously it won't be that high. We'd have to do something else, and there's other tricks that we could play to minimize the G-force to something less than 6 times Earth's gravity. So which is still large, but much more friendly to human beings.
So Grace, you explained the other day that you put your technology through 2 types of tests. And one is load testing, that you take the parachutes and the SIAD through a load test over at China Lake. Now the test for this new parachute had to go through a similar test that the other parachute went through last year, and that's at China Lake. And we have a video of that, and the video is we break for Mars, but the video you see right now is for the SIAD. It's the sled test for the SIAD, which is the inflatable donut you guys were talking about.
Yes, the great thing about using a rocket sled, you can actually do the test and actually get, even though you're not at high altitude, the air is still pushing on. You can actually inflate this this Syad into these conditions and make sure that the Syad itself is strong enough and its attachment to the vehicle is strong enough to withstand the pressure of the air blowing on it as it's moving at these Mars supersonic speeds.
So that's what Grace was talking about. You have a launch vehicle and you can only fit so much, or a size of a heat shield so big. And so by having an inflatable donut, you just increase
the area.
That's right.
So the trick for landing at Mars, it's all about slowing down. I mean, the real key to be a successful landing is slowing down before you hit the planet. That's an obvious detail, but on Mars, with the atmosphere so thin, it can only do so much. There are other tricks we can play. There's other types of inflatable devices. We have multiple parachutes for larger scale, and we can even use supersonic retropropulsion, which is something that is being tried and tested right now as a way of also adding to the ability to slow down. And so Mars provides a lot of challenges that we don't have on Earth because we live in such a thick atmosphere. Right. And because of that, we have to pull out different tricks that we use on this planet.
So speaking of your test tricks, let's go to the video of We Brake for Mars. So this is your load testing. This is the testing you do at China Lake to make sure that your parachutes are strong. So let's take a look at that right now.
Hi, my name is Mike Meacham. I'm an engineer here at the Jet Propulsion Laboratory, and I want to talk to you about some of the technologies we're developing for landing bigger and heavier things on Mars, one of which is a much larger supersonic parachute. When we land spacecraft on Mars, we're going extremely fast. We have got to slow down, so we use a parachute, and we use a really big parachute. To make these large parachutes, you have to test them before you go. You need a way to apply the same load that you're going to feel on Mars, and you need a way to do that here on Earth. In the past, we've always used a wind tunnel, but the parachutes themselves are getting so large they don't fit in any of these wind tunnels anymore. We needed a way to apply the same type of wind in a controlled way, and we had to get outside of the building. If you want to go to Mars, you want to go big, then you've got to test big here. You've got to be a little crazy sometimes if you want to do the crazy things. The crazy idea we came up with was to attach it to a rocket sled and have that rocket sled pull it around a pulley with a huge 1 kilometer long rope. And the way you have to do that is extremely complicated. Remember that game Mousetrap when you were a kid, when all these little mechanical things had to happen in sequence? This test is a lot like that. There's a whole bunch of stuff that's got to happen in sequence, one after another, for us to be able to test this parachute. First, a Nighthawk helicopter's got to pick this parachute off the ground inside of a bag. Underneath that's an instrumentation plate. Underneath that's almost 1 kilometer of big, heavy rope. At the bottom of that rope is a 2-foot-long steel bullet. It weighs about 100 pounds. That's all swinging up in the air underneath this helicopter. At the bottom of that bullet is a fishing line, a smaller nylon line that goes another 400 meters or so, all the way down to the ground, through some rollers, down through some pipes, around a pulley in the back of the sled, attached to a 300 horsepower winch. That winch is turned on all the time, pulling on this parachute. The helicopter releases the parachute. The winch spools up, sucking the parachute down towards the ground and maintaining tension through the whole line. Our parachute's now inflated. Our winch is still spooling it in, and it's pulling that bullet right down to the ground through all those same rollers, same pipes, into the back of the sled. As soon as that bullet latches into the back of the sled, we've got the parachute. We cut away that fishing line, turn off the winch, light the rockets, and now our rocket sled is pulling our parachute down toward the ground around a pulley. And that's our outdoor wind tunnel. Okay, so you're seeing the parachute rip, right? It looks bad. It's not as bad as it looks, because really the point of these tests is to find these flaws. We want to see how far we can push these parachutes. We want to see what's wrong with them. And more importantly than anything, we want to see if it happens here on Earth before we spend all the real big bucks and go to Mars.
All right, so we got another parachute and we put it through a similar test?
Yep.
We did. And how did it go?
It worked great. In fact, we took the test to even higher forces using this rocket sled to pull this thing down with this giant pulley. And the force was high enough that we took it even to the point where it actually failed, which is we wanted it on purpose.
Okay.
Just we really yanked on it hard to see what point by pulling it harder and harder and harder it would actually break, and we found it was way higher, much higher than what we'd be seeing, knock on wood, with this with this test in Hawaii when we do it this in June.
So seeing that we had a successful test with the parachute, that enabled you to install that parachute in this test vehicle, and it's in there right now.
It was the last thing they put in. And we were waiting for the results of that test to be able to decide whether or not it was worthwhile to go ahead with the Hawaii test.
So this vehicle is loaded. It has the SIAD, it has the parachute, it's pretty much ready to go.
Yeah.
All right. So we see that the spin test is getting going. Can you kind of describe what's happening in here right now?
Well, one of the key things about if you're going to control a vehicle by spinning it, you better make it a decent top. You know, it's a spinning top, and if the top is out of balance, the top will wobble. Well, we don't want this vehicle to wobble. We want it to fire once you spin it up, just 2 seconds after it falls from the balloon, aimed in the right direction, spins up, and we want the rocket to aim true in the direction we aimed it. To do that, the vehicle has to be very well balanced, and we put it on a spin table so we can measure that balance. This table is very special. It can measure the force of the vehicle as it's spinning to see if there's any way that's slightly out of kilter, and so if it is, we can come back and put in little tiny masses to balance it, like you would balance your automobile tire, right. Exactly the same way. So this is like spinning your automobile tire and putting weights on it to make sure that it spins perfectly.
Now, the second decelerator here, besides the parachute, is the inflatable donut, the SIAD. And you have two designs. In fact, we have the images of the two designs you have been working with, and we can bring that up. And there is the SIAD one, which is the inflatable donut, and then you have the SIAD-E, which is very different. You've tested the SIAD-R, right? And that's the one you'll be testing in Hawaii.
We'll do it again.
You'll do it again.
Yes.
But there are actually two types that you're designing.
You want to talk about
that? Well, yeah, the SIAD-E is designed to be even a bigger area and further be able to bring down more payload. But the challenge is that the SIAD-E doesn't allow us to do a full-up test of the parachute. And so because this year we want to make sure we can get a good parachute test in, we are testing out the SIAD-R again. But we are testing again next summer, and who knows what we end up testing next summer.
And the SIAD-R was also put on a sled test, and that was part 2 of We Break for Mars. So let's take a look at that video.
Hi, this is Mike Meacham again at the Jet Propulsion Laboratory, and I want to talk to you some more about some other inflatable technologies we're working on to slow down bigger and heavier things on Mars. When we're coming into Mars, we're going over 10,000 miles an hour, several times faster than the speed of sound. And we have to wait until we're only going twice the speed of sound before we can deploy our parachute. So we wanted to work on some other device that we could inflate when we're going even faster than that, so we could sort of pull the e-brakes when we're coming in. This other device we call the SIAD, Supersonic Inflatable Aerodynamic Decelerator, SIAD. We are able to inflate this around our heat shield, can increase our drag area by sometimes even twice as much as we normally would be. So we saw that crazy test with the parachute before, right? That's in order for us to load up our parachute to the same types of forces it's going to feel on Mars. We wanted to do the same thing with the SIAD. So we went back to the same track. We had to make a whole new rocket sled. It's a huge one. It's bigger than a house. It weighs 50,000 pounds. So we strap a bunch of rockets to this huge sled. So we drive this down the track, going about 250 miles per hour, and we inflate this SIAD, and we study all the different things that are going to happen to it under this same aerodynamic load. The atmosphere on Mars is a whole lot thinner than the atmosphere we have here on Earth. There's really only one place you can go to test your devices in a relevant environment, and that's way up in the sky here, the upper atmosphere. Pretty soon, we're going to go out to Hawaii to a facility they have there. We're going to take a balloon that's literally the size of a whole football stadium. It's going to pick up our test vehicle. It's going to go up about 120,000 feet into the upper atmosphere. Our test vehicle is going to drop off the balloon. It's going to spin up like a football for stability, shoot sideways across the sky with a huge rocket. Our rocket's going to bring us up to about 4 times the speed of sound, where we can test our SIAD and our parachute in the same exact type of environment that they're going to see on Mars. As crazy as these tests sound, they actually performed them over 40 years ago, and we've been using that technology since then to land rovers on Mars. But it's time to go bigger. We want to land astronauts and bigger payloads on Mars, so we want to see just how far we can push this technology.
right, we're tuning into the spin test once again. And Grace, Rob, how fast is that spinning? It goes...
Yeah, with about 20 RPM.
And how fast do you need to get it to know that things are good?
This is it. I think we're right up at that speed right now where we can measure the tolerances of the uncertainty as it's spinning. And this is about the speed it spins after our spin-up rockets speed it up, fire, to just before the big solid rocket bolted to the middle. It's not, the solid rocket isn't here right now, but it would be right in the middle where this thing is attached. And those rockets would, when that rocket fires, that spinning just keeps the orientation just right, so we know exactly where it's going to land as it fly up into the sky, and make sure it goes to where we want it to go.
So keeping it at this speed keeps it in the direction that you want it to go and straight where you want it to go?
Exactly.
All right. So we've done this testing, and Grace, you were telling me that you do two types. You do the load testing, which is what we do out at China Lake, and then the big test. The one that makes everybody sweat bullets is the one that is in Hawaii. And we have some video of the PMRF. Tell us why you go out to this range every year.
So the two, as you mentioned, we are testing two key characteristics for these parachutes and for the SIAD. One is the loads, and that's where we can go to China Lake to do it. And that's a pretty elaborate test, but it's the lesser of the two in terms of complexity and cost. And so we want to make sure we can be successful there before we go for the next test, which is the supersonic test. And we chose Hawaii for its location, getting its wind conditions. We have a higher likelihood of getting the conditions we need for a launch off the balloon. Its facilities, the infrastructure there. There's a Pacific Missile Range facility there that is basically set up to be able to run tests like missiles and our balloon launch. And we picked the westernmost island of Kauai and the westernmost coast so that we have the space of the ocean to be able to give us the kind of open area that we need. So in Kauai here, as you see here on the screen, we use their runway as the area to set up our launch tower and lay out our balloon and then inflate it up so that it can lift up and carry over the ocean. We have the command control facility here that the range has. They operate the whole operations, and this is where our captain, the captain of the range sits, and key members of our project staff sit to help support him. The rest of our project team is in this other building here off a few miles down. This is where our balloon operations team sits and our test vehicle operations. We get the data down and we can see how the health of the balloon and the test vehicle is doing as we are carried up to the upper atmosphere and commanded to get ready for the final drop. And then here we fly over even further down is where this is Makaha Ridge, where the antennas are set up, and that's where the balloon and the test vehicle sends the data down, telemetry, video, so that it gets fed back into our control centers.
So you're ready to go through all of this all over again pretty soon?
Right. That's right. I think we've figured out a pretty great way to test out these supersonic decelerators up in the upper atmosphere. We've outgrown wind tunnels, and so by using the upper atmosphere we have a lot more opportunity to test future technologies. And so given the test last year and then again this year and next year, we'll be able to learn more and more about these new technologies.
And the Navy has been wonderful for both at China Lake and at PMRF in helping us get this work done, because it's very complicated. It's very unusual for the stuff that they normally do.
We can see how complicated it is.
Yes, it's a multi-organizational team, and the balloon team as well.
Oh,
you know, they're experts in this field, but launching what we're doing here is a first for them as well. And so learning to work with the Navy and the balloon team and Wallops, who has a lot of range experience as well with JPL and what we do on Mars, it's been a great melding of all different organizations and cultures and putting together something pretty cool. And Langley with their analysis, that's absolutely right.
All right, so are you ready for some questions?
Sure.
Okay. How much pressure is needed to force the device to inflate?
The actually surrounding donut, the SIAD, only needs a few psi, somewhere between 5 and 10 psi to get it to its inflated condition, to fight off the pressure of the wind. It's still a lot for soft goods. For example, the airbags that we use to bounce Spirit and Opportunity on the surface of Mars, and Mars Pathfinder, was was less than 2 pounds per square inch. So it's a so this is actually a pretty stiff rubber tire. Actually, it's not rubber. It's made of Kevlar and other very strong fabrics. But that's pretty stiff.
But in the lower atmosphere, right, you don't need a whole lot.
That's right.
Yeah.
Okay, here's another question. Can a parachute be created with a frame that unfolds with the chute and then locks in place to hold it?
I like that idea. I suppose you could do that. We haven't figured out how to, we don't know how to produce an inflatable structure that would do that. But I think I like the idea of a controlled inflation process, and that's actually a really good idea. Maybe whoever thought of it should write it down.
Engineers on our social media. Okay, here's another one. Is there anything in place to control the RPM once it is actually being used outside of testing?
Okay, so the question so our vehicle spins to control its orientation, and that's how Mars Pathfinder, Spirit, and Opportunity all landed on Mars. They spun about 2 revolutions per minute. However, Mars Science Laboratory did not spin, and neither did the Phoenix lander. And the reason is neither did the Viking. They could use thrusters and orientation to get themselves control. So you could use rockets, and we could have used rockets to control the orientation, use small thrusters to keep it pointing the right way, but that would have been more complicated and more expensive. Using spin-up rockets was a very effective, cost-effective, and pretty simple way to get this vehicle on the right track.
Next question is it possible for a SIAD-equipped vehicle to hold an angle of attack and depart from ballistic trajectory on re-entry?
Great question. Another great. Some engineers are coming.
Yeah, I think so.
Yes, in fact, so think about this. For the SIAD, when we do our entering of Mars and we're controlling it, we're using something called that we use in the days of the Apollo to steer the vehicle toward its landing site. We use again these thrusters to help control the vehicle with a center of mass offset to basically make giant S turns in the sky, so that we make sure that we land in our landing site. In the case of, it was Gale Crater for Mars Science Laboratory. If Mars Science Laboratory had a SIAD, we could continue to do that, but we don't really have to. The reason is, almost by the time we open up the SIAD, we're going at about Mach 4. By then, it's slowed down, because almost all that all that steering is done when you're much faster speeds, between 5 and 20 times the speed of sound. So by the time we've got to the point of wanting to open the SIAD, we're already on a direct target to our landing site. So we really don't have to do the guidance while the SIAD. But you could. There's no reason why you couldn't continue controlling the vehicle even with the SIAD open, provided your thrusters are there and working.
Is that something that could be eventually designed into one of these projects, or is just it can
absolutely.
be?
Oh yeah, in fact, it's no problem at all, because as long as the thrusters can have a clear view of space behind the vehicle. Remember now we've lopped off the back of our space capsule. Right. That's where the thrusters would be. And so the SIAD wouldn't be in the way. We could be able to continue to use those thrusters even with the SIAD present. But again, I don't think we need to, because by the time the SIAD opens up, we're already on a direct path. The guidance process is pretty much over by the time you get to the slow speed of 4 times the speed of sound.
So let's regroup and take a look at what you're going to be looking at for this test in June. What will your focus be on this particular test?
Well, first of all, we'd like this test to be as exquisitely perfect as the last test. I mean, one of the things that almost shocked us when we did the last test, when we were watching it, the spin thrusters, which got it up to that speed, did such a perfect job of exactly speeding up to the right speed. And then when the main rocket, the Star 48 rocket, was done, it came to almost complete stop. And it was unbelievable. It's because this balancing process was so exquisitely well done. I would love to see that, hope that works just as well. We can't say for sure. There's a lot of risk in this thing. This is a complicated vehicle. Things could go wrong, and we could have a failure somewhere along the line. But if everything goes just like it did last time, the real trick is to get the next step that didn't happen last summer, which was getting that parachute all the way through the inflation process and without tearing, So so we can get to the point of full inflation without the parachute failing. And now we can see the other part of the test, which is what happens when you're going supersonic and you have a fully inflated parachute, because that's really the crux of the question. Once the thing is open, we have a lot of very complicated computer simulations that tell us what the parachute should do. One of the things it should do is we expect it to breathe like this as we go supersonic, as it's slowing down. There's something called area oscillation, whereas the interaction between this heat shield, the forebody, producing kind of pulses of pressure which affect the shape of the parachute as it's slowing down. Once it's below the speed of sound, then we expect the parachute to be a happy, normal-looking parachute. It'll just vibrate around a little bit, but it won't be doing this funny squid-like dance that we expect it to do under supersonic conditions. So that actually lasts for a few seconds, but we like to see all that when we do this test.
And in light of that,
instrumented more than we've ever instrumented any other
Yes.
test. So I think all the engineers and scientists and researchers have been chomping at the bit to get this data, because we have videos, we have telemetry, we have load cells, sensors, everything to give us all the information we need to really understand what's going on.
and you're approaching it differently. You're observing it differently this time because you are focusing on that parachute. You were saying that you've stationed cameras in different places this time.
That's right, and we even have a 3D GoPro set up this time to maybe capture a little more information from a 3D point of view.
Yes, we'd like to be able to reconstruct the shape of the parachute, because although you have some great video, high-speed video, you really can't, it's hard to tell depth by looking at these two-dimensional images. By having two views from two different cameras synchronized, we can actually put that in a computer and reconstruct the shape as it's going through this process of inflating, and even afterwards when it does, which I believe will do this kind of breathing motion as we'd expect this large parachute to do. So we'll find out.
So one more time, this parachute is a disc or ring parachute?
This is a fully ring sail parachute. They're all rings going all the way out to the side. The ones at the bottom are full up. They look like little miniature sailboat sails. That's why they're called sails. But they're really all a bunch of concentric rings. There is no disc in this parachute, which means there's a lot more concentric structure to hold it together, and because of that, we expect this parachute to be much stronger than when we did last summer.
So you're purposely using a ring versus a disc because
we think that's probably a better. We should have done that. Probably should have done that the first time around. We didn't have the tools when we first started. We since developed the tools since last summer to figure out really what is really going on with the strength and shape during the inflation process.
But again, that first test was more of a shakeout of the test.
Yeah.
You were putting in the parachute and the SIAD sort of as we
Extra
can't.
credit.
Yes, and so.
Well, we got more than extra credit. we actually got a great test, and we learned so much, even though it didn't work.
Right.
We could follow the trajectory, the shape of the parachute. We could see what the suspension lines were doing as they were opening up. We could watch the parachute go from its closed configuration to the open configuration. Incredible detail. We could see almost down little tiny patches on this massive parachute and make out every little nuance. We could even see each of the 96 suspension lines. We could see what they're doing, and it was a wonderful test for us to learn how inflation happens. Because here's the thing. We're testing supersonic parachutes. Where are we doing all our supersonic inflation tests? At Mars. Do we have cameras, do you have cameras to see the supersonic inflation? Do we have high speed? No, we don't. We haven't had that. We just open them and hope that it worked. In fact, one of the reasons we take pictures from orbit looking down our vehicle with the parachute open, so people like me can find out whether or not these parachutes have been damaged. How well does it work? Because we really don't have that information otherwise.
All right, so let's recap what we're doing here today. Grace, explain to us why we are doing a spin test today and what's happening in the clean room one more time.
Yeah, as we said earlier, right, it's very important that our vehicle is balanced and that we can have a true trajectory. Once we light that Star 48 motor, it's taken off, right? And if you're wobbling, you're going to go all over the place. In fact, something I didn't mention earlier is a key part of our operations is the recovery. Once it splashes down in the ocean, we want to be able to bring it back and inspect the parachute and look at what happened to the vehicle. And so And that's part of our trajectory prediction too. Once we expect it to splash down in a certain place, and so that our recovery boats can be positioned correctly and go in and recover. And so that's all part of making sure we have a well-balanced vehicle here.
And before we go, here's one more question from Twitter. Assuming the fuel levels are constantly changing, how do you maintain balances spinning with the changing mass?
These are solid fuel.
These are
the trick is, that's right, it's a solid fuel vehicle, so we know how the fuel is being used up in the solid motor, and we know the distribution of mass as it's flying, and it all stays right down the middle. Now there's some variation, so we did expect a little bit of wiggle, but that's one of the things we wanted to find out last summer. Well, how well does this Star 48 work by itself, spinning up in under these kind of conditions? And it seems not to have much. I think the term is mass, where the movement of the masses on the vehicle was very small and stayed right about the center. So it started off as a top, and it ended up as a top all the way through.
That's the way you wanted it.
Yes, exactly.
All right. So wrapping up things, let's give a status report. How much more testing are we looking at, and when do you pack up and head over to Hawaii?
Well, from an operations, we pretty much completed our testing. In fact, we're going to report out on that in a couple of weeks and show that we're ready, at least as we can be at this point, and we're going to go out to Hawaii and hook up with the rest of our teams and practice when we're out there with the vehicle and get ready for game day. And I do want to do a request out to our audience out there that one of the challenges, besides us being as ready as we can, is that we need the cooperation of the weather out there. In fact, we waited days to get a good wind day. So for all our watchers out there, if you can also wish positive thoughts on getting a good balloon conditioned days for us, then we're going to have a good test this summer.
That was a real issue last year, wasn't
it?
We had to regroup and change dates for a couple of different tries.
Right. We have no control over the balloon. We can predict where it's going to go with some really, a day in advance with some really remarkable accuracy. But that prediction and the actual flight better be where we want it to go. And so we have to wait until the trajectory, our expected path, is the right way and out to sea and not back inland.
Okay, and the period of the test, what are we looking at? What dates?
We're shooting for within a 2-week period that we can find a good day to launch. But if we saw last year, we didn't find a good day in those 2 weeks, and we had to go home and come back a week or so later and try again.
So the 2 weeks, June 2nd?
Through the 12th.
June 2nd through the 12th. Okay, so we will be hoping and praying to the Hawaiian weather gods that we get low winds and good weather.
Thank you.
All right. Well, if you want more information about LDSD, take this URL down. It's http://www.nasa.gov/pages/TDM/LDSD. And that's it for today's spin test and our Ustream and Periscope and NASA TV. Thanks for joining us.